We did it. We're finally in calculus. Chapter 2, Limits. We begin calculus. Hey, so what is a limit? Well, here's a quote for you. If the y values of a function get closer and closer to some number, let's call that number L, as the x values get closer and closer to some number, and we're going to call that C, then we say the limit of f of x as x approaches C is L. And we write the limit as x approaches C of f of x equals L. This is our limit notation, and we're going to be using this for the rest of the year. So what does this mean? If the y values get closer and closer to some number, as the x values get closer and closer to some number, then we say the limit of the function, the limit of f of x as x approaches C is L, and we write the limit of f of x as x approaches C is L. All right? Now, I imagine that for many of you, this still doesn't make any sense. So I will say, let's take a look. The limit as x approaches 1 of x plus 2. Okay? So there's my function, and the x's are headed towards 1, and I want to know what value the y values are approaching. So from the left side, I could use a table, x plus 2, and put in 0.8, 0.9, 0.99, 0.999. Okay, these values are getting closer and closer to 1. X is approaching 1. The y values, 2.8, 2.9, 2.99, 2.999. The y values are approaching some number. What about from the other side of x equals 2? From the right. X, we have x plus 2. How about 1.2, 1.1, 1.01, 1.001? That'll give me 3.2, 3.1, 3.01, 3.001. What number are the y values approaching from both sides as x approaches 1 from either side? Notice how our y values are approaching some number, and to me they look like they're approaching 3. So I could say over here the limit as x approaches 1 from the negative direction, right? We're coming up from 0 and we're headed towards 1 from this way, of x plus 2 is 3. And over here I could say the limit as x approaches 1. This time we're coming in from the other direction, 1.2, 1.1, 1.01. So coming in from the positive side of x plus 2 is also equal to 3. And since these limits are the same, then we can say this. Since the limit as x approaches 1 from the negative side equals the limit as x approaches 1 from the positive side. We say the limit equals 3. The limit as x approaches 1 from both sides. It's just as we approach 1 of f is 3. Okay, so we know that limit is 3. So what are we talking about here? As x's get closer to this x value, the y values are approaching this number. Remember, the limit is the y value. The limit is the y value we're approaching as x heads towards c. All right, so a limit is a y value. It's the y value that we're approaching. Now, I gotta say though, that limits do not always exist. They don't always exist. For a limit to exist, the y values must converge on L from, regardless of whether x approaches c from the left or right. Okay, so, and our definition, the one I put up before, but maybe a little more general, the limit as x approaches c from the negative of f of x needs to equal the limit as x approaches c from the positive side of f of x. And if that's true, then the limit as x approaches c of f of x exists and is whatever that limit is. All right, so I'm not sure you're still quite comfortable yet with this whole thing about limit. So let's think about this graphically for a moment. We just looked at this situation. Here was our function y equals x plus 2. And I was asking about 1. And asking the question, well, what is the limit as x approaches 1 of x plus 2? And what we saw is, as the x values got closer to 1 this way, these y values got closer and closer to 3. And that was the limit as x approaches 1 from the negative side. We saw them heading to 3. But when we came in from this side, these y values were also approaches 1 from the positive side of x plus 2. These values were getting lower and lower until we were approaching 3. So as x approached 1 from either side, the y values approached 3. That's how I understand the limit. The limit is what the y values are approaching. Okay? Now, how do I evaluate limits? We're going to have a number of things on this list. We saw the first method already, use tables. I hate using tables. I don't want to use tables. If I can avoid using tables, I'm going to avoid using tables. Remember the AP exam, half of it without calculator, so I'm not doing a table without a calculator. So what else do we have? Well, 2. We've got some properties and we've got some guidelines. The first is the limit as x approaches c of some constant. The limit of a constant is always going to be that constant. What does this mean? Well, let's think about this. The limit as x approaches 2 of 7. And I'm willing to make a table of this. 7x, I'm approaching 2. So how about 1, 1.5, 1.9, 1.99. How about 2.1, 2.2? What do we see here? Well, we see that this is a constant. No matter what x value I try and use, because there's no place to jam those x's in, this says, hi, I'm 7. Hi, I'm 7. And said a different way, if we looked at the graph of y equals 7 as x approaches 2, what y values am I approaching on this horizontal line? Well, I'm not approaching. I always have a value of 7. So we can say the limit of the constant is going to be that constant. So if someone says, hey, what's the limit as x approaches -4 of 5? Well, that's a constant. And the limit of a constant is the constant. And that's pretty easy and straightforward for us. Okay, next. Direct substitution is my preferred way of evaluating limits. So if I have a limit like x approaches 2 of 3x plus 1, then 3 times 2 plus 1 is 7. The value of this limit is 7. I could do direct substitution and know what that y value was. That's wonderful. I love direct substitution. Okay, direct substitution is the most common approach to evaluating limits. But what happens if direct substitution does not work? If direct substitution does not work, then try using your algebra skills to rewrite the expression. Algebra skills? I have them. Of course you do. You have fabulous algebra skills. Here, let's take a look at this problem. The limit as x approaches 0 of x plus 3 squared minus 9 over x. So let's try direct substitution. I'm going to plug 0 in for all the x's. Okay, so I got 0 plus 3 squared minus 9 over 0. And I get 9 minus 9 over 0. I get 0 over 0. Yeah, so about that, that's an indeterminate form. Indeterminate form means sometimes this is going to be equal to 0, and sometimes a number divided by itself, this is going to be equal to 1, and sometimes, because I'm dividing by 0, this will be infinity, and sometimes this will be 2/3. And how am I supposed to know? Well, it depends on the situation. Whenever we have an independent form, we have to evaluate that indeterminate form based on what situation we're seeing it in. And the easiest way to evaluate an indeterminate form is to use something called L'Hopital's rule, which we're not going to use today. Instead, we're going to cover L'Hopital's rule in the spring. And so all I want you to understand about this indeterminate form is if you get 0 over 0, that's not the limit. And we don't know what that's equal to. So my advice is let's use our algebra skills to rewrite this. Okay, so what will that look like? x approaches 0 of x squared plus 6x plus 9 minus 9 over x. And then what do I do? Well, I can combine like terms and have the limit as x approaches 0 of x squared plus 6x all over x. And then I could factor an x out of the top and have x plus 6 over x and then cancel. Now if I plug a 0 in, I get 0 plus 6 or 6. So in this situation, when we get 0 over 0, that is actually equal to 6. 6 is the value of our limit here. So when we tried direct substitution, it didn't work. We got an indeterminate form. And when we used our algebra to rewrite as x approaches 0 of x plus 3 squared minus 9 over x, we turned that into the limit as x approaches 0 of x plus 6. And so now we can do direct substitution and get 6. So we know that the limit as x approaches 0 of x plus 3 squared minus 9 over x is 6. Don't forget to write sentences. Now, another thing I wanted to say. Do you see how every time I take a step, I'm writing down the limit notation? So here's the thing about that. Until you do direct substitution, you have to keep writing the limit as x approaches 0, x squared plus 6x plus 9 minus 9 over x, and that was equal to the limit as x approaches 0 of x squared plus 6x over x, and then that's equal to the limit as x approaches 0 of x over x plus 6. We cancel those out, and now I'm ready to do direct substitution, and so that equals 0 plus 6 or 6. Only once you've done the direct substitution can you get rid of the limit notation. You leave this limit notation off, this means something completely different, and so minus 1, minus 1, minus 1 point each time. Please do not leave the limit notation off, okay? All right, why don't you see if you can evaluate this limit? The limit as x approaches 2 of x squared minus 4 over x minus 2. Please evaluate that limit. Pause the video, give it a try. Come back if you are stuck and have questions, or if you are done and you want to check your answer. Okay, so when I plug a 2 in, I end up with 4 minus 4 over 2 minus 2, and that's 0 over 0, so we have indeterminate form. So since direct substitution didn't work, the next thing I try is using my algebra skills. So we've got the limit as x approaches 2. That's a difference of squares that we can factor, x minus 2, x plus 2 over x minus 2. And then look, cancel. Now we're looking at the limit as x approaches 2 of x plus 2. Well, now I can do my direct substitution. I can replace x's with 2's as 2 plus 2 or 4. And so I know the limit as x approaches 2 of x squared minus 4 over x minus 2 is 4. This time 0 over 0 was equal to 4. Surprise! Indeterminate form. All right, so how about this one? I'd like to think you're starting to feel a little more comfortable with this by now. The limit as x approaches 1 of x squared minus 1 over x minus 1. Okay, give this one a try. Tell me what that limit is. Show me the work that leads to it. Definitely going to need to see the work. Don't be doing this in your head. Yes, you need to write a sentence. Okay, welcome back. So if I plug in 1, I end up with 0 over 0, and that's an indeterminate form. So I think, well, I better use my algebra skills to rewrite this. X minus 1, x plus 1, x minus 1, cancel. Now I can do direct substitution, and it works. But let's think about what's happening here graphically, so we know what this 2 means. Okay? So if I have y equals this, what does it mean when I cancel out those factors? It means I have a hole in the graph at x equals 1. So 0, 1, negative 1, 0, and we want to be approaching x equals 1. So at x equals 1, there's a hole in the graph. So here's an interesting point. The point doesn't have to exist in order for the limit to exist. See, there's no point here. This is undefined at x equals 1. But that doesn't mean the limit doesn't exist. Remember, we're saying, what y value are we approaching as x heads towards 1? Well, what value are we approaching as x heads to 1 from this way? And what y value are we getting when x approaches 1 from this way? We're approaching the same y value, and we determined that that y value was 2. So this is 2. Please note the point does not have to exist for the limit to exist. The limit is just what point are we approaching. We're approaching the point y equals 2 as x heads to 1. The point does not exist. Okay? That's going to be very important for us, so please wrap your head around it. All right, so we did some samples. We looked at that one algebraically and graphically. Let's evaluate limits by using a graph. Okay, so this one starts 0, 0, and it goes up to here, 1, 2, clink, and then here, 1, 1, and here, close circle, 3. So here's our graph of f of x, and I want to evaluate some limits using this graph of f of x. Okay, so the first one is, what's the limit as x approaches 1 from the positive direction of this function? So, as we approach x from the positive side, what y values are we approaching? Well, this is horizontal, so the y value is always the same, a y value of 1. Now, what about the limit as x approaches 1 from the negative side of this function? What y values are we going to approach as x heads this way? Well, the y values seem to be heading up here to 2. And then I want to ask the question, hey, what's the limit as x approaches 1 of f of x? Well, remember, the limit as x approaches a point only exists if the limit as x approaches 1 from the positive side of the function equals the limit as x approaches 1 from the negative side of the function. If these equal each other, then this is it. This is true. If these equal each other, then the limit exists, and whatever the limit is for these two, this has that same limit. Okay? So what do I notice here? Well, if I'm asked the question, hey, what's the limit as x approaches 1 of this function, I think about coming in from the positive direction at a value of 1, coming in from the negative direction at a value of 2. Are we approaching the same y value as we get closer and closer to 1 from these opposite sides? And the answer is no. 1 doesn't equal 2. These aren't approaching the same value. And so we say does not exist. Okay? And you should definitely get in the habit of writing a sentence. And so we could say, the limit as x approaches 1 of f of x does not exist because the limit as x approaches 1 from the negative side did not equal the limit as x approaches 1 from the positive side. Okay? This, don't box it in, this is the sentence that I'm talking about saying, right? I don't want that. The limit does not exist. You know, yeah, you could do that, but really, you need to explain why doesn't it exist. And it's nice to notice that that the limit doesn't exist, but if you're going to make a statement like that, you need to back it up with some evidence. Okay? All right, so we've got the same graph. Let's see if we can answer another limity question. How about what's the limit as x approaches 3 from the positive side? Well, there's 3, there's 1. This is me approaching 3 from the negative side. What about approaching 3 from the positive side? Can I approach 3 from the positive side? I cannot approach 3 from the positive side because there's nothing over here. The graph stops at 3, so this limit does not exist. But if I was talking about the limit as x heads to 3 from the negative side of this function, as I come in this way, what y value do I have? I have a y value of 1. Okay. Now, how about this? There's 1, 1, 0, 0, and here, this way, it's 3. So here's a graph of f of x. Okay, it's a piecewise function, and I want to evaluate some limits. So what can we say about the limit as x approaches 0 from the positive? Well, as x's get closer and closer to 0, yeah, I know I'm up here, but then I jump down here. What y value am I approaching? I'm approaching 0. What about the limit as x approaches 0 from the negative side of the function? Well, now I'm coming in from this direction, and I seem to be approaching a y value here. And since these limits are equal, since the limit as x heads to 0 from the positive side equals the limit as x approaches 0 from the negative side of f, you've got to tell me the limit of what? I need that f. Equals 0, then a limit as x approaches 0, not from the left or right, just the limit, is 0. So these two limits have the same value. That value is 0. Because these have the same value, the limit as x approaches 0 exists and takes on the same value as these two one-sided limits. Okay? All right. Now it's your turn. How about the limit as x approaches 1 from the positive side of this function? What's that going to be equal to? You try this one. Okay, did you say 3? I hope so, because as I approach 1 from the positive direction, I seem to be approaching a y value of 3. What if I approach from the other direction? X approaches 1 from the negative side. Well, as x approaches 1 from this way, my y values seem to be approaching 1. So then, does this limit as x approaches 1 of f of x exist? No. And why not? Okay, so I'm going to say the limit as x approaches 1 of f of x does not exist because the limit as x approaches 1 from the positive side of the function does not equal the limit as x approaches 1 from the negative side of this function. All right, so the limits from both sides have to be the same in order for the limit at the point to exist. All right, how about this one? That's an open circle. That's an open circle. Open circles here. That's 2. That's 2. That's -1. That's -1. Close circle over. That's -2. Okay, so here's g of x. And I want to ask you some questions. Okay. First question. What's the limit as x approaches 2 from the positive side of g of x? That's right, we're approaching from the positive side of 2, and the y value we're approaching along is 2. How about the limit as x approaches 2 from the negative side of g of x? What do you get for that? As we head towards 2 from the negative direction, what are the y values approaching? And the y values are also approaching 2. So then, what about the limit as x approaches 2 of g of x? Well, because these limits are the same, and they're both equal to 2, the limit at the point must also be equal to 2. Some of you might be saying, but Mr. Euclid, the point doesn't exist. The point doesn't have to exist there for the limit to exist. In order for the limit to exist, we just need the left and right side limits to be the same, okay? If I ask the question, hey, what's f of 2? You say f of 2 does not exist. Oh, yes, it does. It's down here. 1 is the value of that limit. Okay, I mean the value of the function at 2. At 2, that closed circle point at 2, 1, that's where the function exists at 2. Is that the same as the limit? No, and I don't want f, I want g. I will say that g of 2 does not equal the limit as x approaches 2 of g of x. Okay, so the limit can exist even if the point has a different value, or even if the point does not exist. Even if that point does not exist, I can still have the limit of the point, because the limit is just what y value are we approaching. Okay? How about this one? The limit as x approaches -1 from the negative side. What do you get for that? As we approach -1 coming in from the negative direction. What do you get? I get -2 because as my x values get closer to -1, my y values are staying at constant -2. What about the limit as x approaches -1 from the positive side of this function? Well, as I approach -1 from the positive side, I seem to be writing down along here, and that seems to be approaching that y value. Okay, so then what's the limit as x approaches 1 of g of x? That's right, that does not exist because the limit as x approaches -1 from the positive side does not equal the limit as x approaches -1 from the negative side of g of x. All this notation is really appropriate. Don't say a thing like the limit is the same from both sides. In your brain, that might make sense. In my brain, that doesn't make sense. You know what my brain is saying? The limit. The limit of what? What limit are we talking about? Of what? If you don't tell me, I don't know. If you don't tell me, the reader in Kansas City who's going to be giving your AP exam a grade will say, they don't know what they're talking about here. And the same from both sides. Both sides of what? Because this is not a true statement at 0. At 0, the limit of g of x from both sides is 0. So you can't use vague language like this. Please use your limit notation and say, look, the limit at the point 1 does not exist because the limits from both sides aren't equal to each other. Don't say vague language. Use your notation to say precise language, okay? All right, so we know that g of -1 does not exist. And what about g of -1? Remember, that's the y value at the point x equals -1. There's -1, there's the point. I know that this is equal to -2, okay? Sometimes the value of the point will be equal to the value of the limits, but in this problem, we have a jump discontinuity here as the y values approach -2 from the negative side, and over here as the y values approach -1 from the positive side. Okay, so again, we say the value of the limit does not, let's put that in red, does not depend on the point existing. Okay, and so for example, if I have this situation, sorry, that's a 1. Let's look at the limit as x approaches 1 of x squared minus 1 over x minus 1. Okay, so if I plug in a 1, I get 0 over 0. It's an indeterminate form. Doesn't help me figure out the limit. If I do some algebra, I can cancel. And now this simplified expression does allow me to do direct substitution, and so I get 2. I do get 2, don't I? Get 2. That was a 2. That was a 1. Okay. Does the point exist? No, we've got a hole in the graph there. That doesn't mean the limit can't exist. As x approaches 1 from both sides, the y values are approaching 2. Okay. Now, we could even have a situation like if this is f of x, and we have a piecewise x squared minus 1 over x minus 1 for x not equal to 1, and then 1 for x equal to 1. So this piece says, I exist everywhere except at 1. That's true. And this piece says, hey, at 1, I take on this y value, the y value of 1. But does the limit exist? Sure. I know the limit as x approaches 1 from the negative side of this function is approaching a value of 2. And I know that the limit as x approaches 1 from the positive side of this function, as we come in from this direction, the y values are approaching a value of 2. And I know that since the limit as x approaches 1 from the positive side equals the limit as x approaches 1 from the negative side, and that limit is equal to 2, I know that the limit as x approaches 1 of f of x will equal 2. You might even want to say a therefore. Okay? So, the existence of the limit, this limit exists, does not require the point to exist, or even if the point exists, not to be filling in that hole. All right? So, last thing I want to look at with you now is this. A couple of problems. From homework number, is it 25 or 26? I think it's 26. Yes, a couple problems in assignment 26 ask about average rate of change and instantaneous rate of change. Examples on pages 59 through 60. In fact, they're examples numbers 1 and 2. So take a look at those. Let's say that we know average rate of change is simply slope with units. Okay? So if I have, let's say I have this function y equals 16t squared, and I want to know the average rate of change in y on an interval 1 to 3. Okay, so, oh, and I need units, so how about t is seconds and y is height in meters. Okay, so how do we do this? Well, average rate of change is slope with units. So average rate of change is the slope on that function between these 2 points. If I'm looking at this visually, there's my graph, y, and I'm going from 1 to 3, and I want the average rate of change or slope. So I need to know y of 3, and that's going to be 16 times 3 squared, which is 144. And I need y of 1, which is 16 times 1 squared, which is 16. And now I'm ready to find the average rate of change. Remember, average rate of change is slope. So my slope will be 144 minus 16 over 3 minus 1. Remember, the units here are meters, and the units here are seconds. So what do we get? We get 128 over 2, or 64 meters per second is the average rate of change in y on 1 to 3. Okay? Yes, I need to write all this. Yes, you should be writing all this. Okay, so that's average rate of change. Average rate of change is simply finding the slope between those 2 points. Okay? All right. Now, instantaneous rate of change, they ask us to use a certain formula. See, if you actually read the unit, you'll see the formula. Instantaneous rate of change. So they're saying this. We know the instantaneous rate of change would be the slope at a point. We're going to be really challenged to find the slope at a point. But I know it's a change in y's over a change in t's, or a change in x's. And in our problem, we're going to say the limit as h approaches 0 of 16 2 plus h squared minus 16 2 squared over h. So what is this? This is how I'm supposed to figure out the instantaneous rate of change. This is how I'm going to figure out the slope at a point. Well, it doesn't make a lot of sense to me yet. Can I do direct substitution? If I plug that 0 in there, I'm going to have 16 times 2 squared minus 16 times 2 squared. That's going to give me a 0 on top. H approaches 0. I have a 0 on the bottom. I've got 0 over 0 and sad face. So we need to bust out some of our algebra. Okay, so this limit is going to be equal to the limit as h approaches 0 of 16 times 4 plus 4h plus h squared minus 16 times 2 squared all over h. Okay, now if I do direct substitution, it still doesn't work. So let's do some more algebra. The limit as h heads to 0, 64 plus 64h, 64h plus 16h squared minus 16 minus 64 all over h. So these can cancel. And now I've got the limit as h heads to 0 of 64h plus 16h squared over h. And I notice that I can factor an h out of each of those. The limit as h approaches 0 of h, 64 minus 16h all over h. And then these can cancel. And now I can plug in my 0 for h and get 64. Okay, so the slope at that point is 64. Now remember, we did the average rate of change, and what did we come up with? We said that was going to be 128, no, it was going to be 144 minus 16 over 3 minus 1, and we said that was 128 over 2, and that was also 64. You know, it's interesting that both the average rate of change and the instantaneous rate of change is 64, because that definitely doesn't happen all the time. Okay, so using this same y equals 16t squared, y equals 16t squared, would you please find the average rate of change on 2 to 5? Please find the average rate of change on 2 to 5. Pause the video, give it a try, come back when you're done, or if you're stuck and want to see how it's done. Okay, welcome back. So average rate of change is slope. And so in order to find the slope, I need y of 5 minus y of 2 over 5 minus 2. And how will I find y of 5? Well, I'm going to plug that 5 in for t. So I have 16 times 25, which is 400. And to find y of 2, well, I've got to plug a 2 in there now. 16 times 2 squared is 4, and so I have 64. So this becomes 400 minus 64 over 3, or 336 over 3, which is 112. Don't forget our units. Average rate of change is slope with units. We have meters on top and seconds on the bottom. These are meters up here. These are seconds down here. That's our average rate of change. So I might want to write a sentence saying the average rate of change in y equals 16t squared on 2 to 5 is 112 meters per second. Okay? But if I were going to use instantaneous rate of change to find slope at a point, then I'd be looking at, and let's say we want to know the slope at 3. So to find the instantaneous rate of change at time equal to 3, we're shown in the example problems to do 16 3 plus h squared minus 16 3 squared all over h. Okay. Can I do direct substitution? Well, put in a 0 here. I'm going to have 3 squared, or 9 times 16. That's 144. And over here I have 9 times 16. That's 144. And 144 minus 144 gives me 0 on top. And when I plug that 0 in there for h, I have 0 on the bottom. Here's another time when direct substitution does not work. So let's do some algebra. H heads to 0 of 16, 9 plus 6h plus h squared minus 144 all over h. And that's going to bring me to the limit as h approaches 0 of 144 plus 96h plus 16h squared minus 144 all over h. So these cancel. And I notice that I can factor an h out of everything. Okay, let's factor that h out. Notice also, I'm writing the limit notation every time, and you need to as well. 96 plus 16h over h. These cancel. Oops, that's an h. Now, when I try direct substitution, I get 96 plus 16 times 0, or 96. So I know the instantaneous rate of change is 96 meters per second at t equal 3. All right? Excellent. So I think you have a sense of how to do average rate of change and instantaneous rate of change. Average rate of change is slope with units. Instantaneous rate of change, I have to use that little recipe that they were using in examples 1 and 2 from the textbook. So again, instantaneous rate of change is a limit as h approaches 0 of f of x plus h minus f of x over h. Or we could have, that's a general form of it, we could have limit as h heads to 0 of f of some number. So we can explore this by plugging in a specific value, or it should even work with just x's. Okay, but that's the kind of thing you might need to bring in if they ask you to find instantaneous rate of change. So what do we know about the limit? Let's summarize. A limit is the y value we approach as the x's approach some number. And we know some things about evaluating limits. First, limits of x equals 2 of 5 equals 5. We know the limit of a constant is that constant. 2. We love direct substitution. When direct substitution doesn't work, the limit as x approaches 3 of x squared. It's going to be 3 squared or not. See, direct substitution, beautiful. If direct substitution doesn't work, we said rewrite using algebra skills. Simplify, then do direct substitution. Well, that's great. We've got 3 methods of evaluating limits, but wait, there's more. There's actually 5. 4 is use tables. You know, go type the function into y1, and then go over to your table feature and type in values that get closer and closer to x equals c to see what y value is approaching. Okay, so we could use tables to do that. And then, finally, we could think about this graphically. You know, when we looked at what's the limit as x approaches 1 of x squared minus 1 over x minus 1, we looked at the graph there and said 0, 1, negative 1, 0. As x approaches 1, the function doesn't exist there because of a hole, but that doesn't mean we can't figure out what that y value is. So limit as x approaches 1 of x plus 1 when I do the canceling. And so I get 2. So I can use graphs, I can use tables, or not to use either of those, but they can be handy and extremely helpful. I can also do direct substitution, and I can rewrite things algebraically to make sure that they work. All right, so that whole thing about average rate of change and instantaneous rate of change, oh my God, we're going to be talking about that all year. Remember that average rate of change is the slope on an interval. It's the slope of a secant. It's the slope between 2 points. So if I have y equals 16t squared, and I want to talk about average rate of change, that's the slope. Average rate of change on y equals 16t squared on 1 to 3 is the slope from 1 to 3. But, and that's the slope of that secant line. See how the secant line touches twice? But if I want to know the instantaneous rate of change at time equal to 2, now I'm talking about finding the slope at this one point, t equals 2. Okay? Sometimes it turns out that the average rate of change, the slope of the secant line, and the instantaneous rate of change, the slope of the tangent line, sometimes they're the same, and often they're not the same. We don't really care if they're the same or not. We just want to know how to compute them. Okay? All right. So that's it for today. Go do the homework and send questions to the group me or bring them up in our live Zooms. Take care, everyone.